So next up is John Karafin. John is the head of Lightfield Video at Lytro. I'm sure you've all seen some of the announcements in the last few weeks. So John will be touching on some of that. So Lytro has been one of the, and probably the only real light field camera manufacturer, certainly in the United States. And they came out with, as Paul showed earlier, just the small Lytro camera a few years back. So they've been on the cutting edge of camera technology for Lightfields. So without that, there you go.
Thank you for the introduction. And I got some claps here. That's awesome. All right. I actually paid them $20 to clap for me, so that works out pretty well. Ah, there we go, another $20. All right, so I am John Karafin, head of Lightfield Video for Lytro. And initially when I was told I would be going last, I was really excited about that. And now I've realized everybody has said everything about Lightfield possible. No, but I have some other really cool stuff I can show. And one of the other things that is really interesting is when we first learned about this event, and who was it, John over there? That was a year ago. So thank you, you're awesome. You get another 20. We didn't think that this was going to be this well attended, so I initially had prepped a whole bunch of really awesome content, and then I was made aware that hundreds of people were attending, plus the media. So now I get to tell you about the types of things that we're doing, according to my GC. But we're going to go into a lot of the things, including the VR, the Lytro Emerge that many of you probably saw the announcement, and we have even let's call them more exciting technologies even beyond that I will start to hint at and tell you the types of things that you can do as content creators with Lightfield. So let me take a quick step back and talk about the past for a moment. And when you really look at the history of photography, and that includes obviously motion picture and everything else, we haven't really had that much of an innovation from the day that it was conceived all the way through today. So for the past, since the early 1800s, we've been looking at the image as a flat representation of the world and looking at it inside of a rectangle. So what we believe at Lytro is that computational imaging is in fact the future of imaging. It will be the next generation of capture technology. And as we go from the film cameras to the digital cameras, then you get into the computational production pipelines. So with that, we do like to say that Lightfield is the future of imaging. And it is not a matter of if it's going to happen. I think after looking at what everybody is presenting at this panel today, it's a matter of when it will be happening. And I can assure you it is happening much sooner than most people expect. So as I was mentioning earlier, while I can't go into a lot of the specifics, I can say Lytro, in addition to the VR technologies, is also working on cinema capture solutions. And it will, in fact, be the highest resolution camera ever designed. And that is one of the things that we are most excited about. My opinion is in Silicon Valley, we're probably one of the most exciting things happening, but I am biased, of course. But let me go into a bit more of that. And I'm going to take a bit of a different approach here. I'm going to actually tell you how a Lytro camera works. So there's a very different approach. You see in a lot of the other presentations where you're looking at light field arrays and you're seeing how they are able to capture the 5D or the 4D, or even some people talk about the 8D and the 7D planoptic functions. Lytro does have a very different type of a technology, and Paul did speak to this briefly. We have something called a micro lens array. And this is the core of Lytro's technology. And what you're looking at here, this, my laser does work. This is the micro lens that was actually included inside of our first generation, the little butter stick camera, where you're looking at literally hundreds of thousands of lenses that are built at the wafer scale, and they get included behind the main lens in front of the actual silicon, the actual imaging sensor itself. And these are quite literally hundreds of thousands of lenses that are taking the light and then breaking it apart. And I'm going to show you exactly why that is important and what you can do with that. So again, to bring it full circle, you can take the entire array of cameras, these huge, very big, very complex systems with lots of lenses, lots of cameras and everything. And you can, in fact, put that into a single lens, single sensor design by using the microlens array approach. So this is how the camera fundamentally works, and it has obviously been very simplified here. So just to try and make the visuals a little easier to digest, because optics is actually quite complex. But you have a main lens here, and behind it you actually have this micro lens array. Now in this example, just to make it nice and simple, we're making it in what we call a square packed grid. In reality, you can do that or do something called hex packing, which actually increases resolution, increases the sampling. But that's getting way too rat hole and complex here. But when you look at it, behind that, it's actually close to, at the focal length of the actual microlens itself, are the physical pixels. So let's actually break that down even further. And if you look at just a single lenslet among the full microlens array, what you're actually doing is taking the light from the main lens and you're re-imaging the exit pupil, which is what is giving you the full amount of the angular information. So if you have light that would have initially focused here, you're fundamentally getting the theta and the phi directionality of the light itself. And this is what gives you that 4D functionality. It is also what is giving you virtually the holographic capture. And that is what Lytro cameras actually are. It is a holographic capture system. So a couple of really important points, and this is actually animated, and I'll get into that because it's just really cool, so I'd like to show it. So again, very simplified here. These are the microlenses. This is your, again, thin lens equation of what happens when you re-image from the microlenses to the sensor to the main lens. To tie it all back to how to think of this as content creators, at each of these junctions here is something that we call a sub-aperture. So what happens is you can think of these converging rays at the entrance pupil is divided by the number of pixels behind each microlens. So again, for simplicity, if you have this many microlenses and you have, in this example here, it's 6 pixels behind each microlens. In reality, it's far more than that. You end up getting a 6x6 grid of sub-apertures, which are the actual full resolution images. And it would be the same thing as if I had placed a camera and a lens right here, 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 and here, and then multiplied that 6x6. So if you think of things like the Stanford camera ray and any of the other camera rays that you have seen, it is one and the same by virtue of the fact that you are reconstructing individual camera images at these positions in space. The other thing that is really important here, and ooh, it's animated, I love it. Okay, when you look at this, this is showing the relationship between the size of the lens and the actual baseline that forms. So I get a lot of questions whenever we're showing how the technology works, what it does, in terms of what is the full baseline or what is the coverage I get from the amount of parallax from the system. And most people believe that it has something to do with the size of the sensor. In fact, it's not. It's actually only the size of the lens that determines the actual parallax in the system. So the larger this entrance pupil becomes, the greater the amount of parallax that forms by virtue of having these points get larger in separation from each other. Does that make sense? A lot of nods. I love it. Okay, great. So this is obviously how you can get stereoscopic imaging from one single lens. This is how you're able to do basically the very dense sampling from the light field itself. And this is how every single Lytro camera works. The other thing to consider from a resolution standpoint, the easiest way to think of each of these microlenses is to consider them one pixel of the final image. It's not, again, quite that simple. There's a lot of sampling. There's a lot of things to get the depth of field and do a lot of additional resampling from the light field. But when you look at each one of these, if you think of it as a single pixel, you can understand now that this is the angular resolution. So the more pixels that you put behind each of these microlenses, the greater your refocusable range has become. Now, of course, that means you need smaller pixels and higher resolution. Lots of trade-offs that have to occur there. So just for a moment now, with all of that information, let's now put ourselves inside of the camera so I can show you what that actually has to do. All right, I'm glad you guys laughed. I wasn't sure about that one. So now let's go inside the camera. Put yourself looking behind the sensor itself. So now we're behind the sensor. The microlenses are actually in front of the silicon here. These are the sub-apertures that form. Right? Again, overly simplify, and they end up not being quite this linear, of course. But again, that point that I was making earlier about these pixels, so if you look at this particular image, and if I go through a couple, and you see what pixels are being sampled from, this is how you generate that subaperture. So each one of these subapertures is equivalent to, just a simple equation, again, not exact, if I had a main lens here, and this is the main lens that's being intersected by all of these virtual subapertures, let's call it an f2. If I have 6 pixels behind each one of the microlenses, that's effectively an aperture size of an f12 lens that's divided across the entire entrance pupil of the system. And that is how you're able to relatively easily, just from a very simplistic way, the thin lens type of an equation, figure out what are the quantity of the subapertures that form, what is my array size. So if I had 100 by 100 pixels behind each microlens, that would form 100 by 100 subapertures, right? And then if I had 100 pixels and an f2 lens, then you could think of that being f2 times 100, and that is what effectively gives you an f200 lens. So that's, again, getting a little bit rat-holed and a little bit too technically detailed, but to give you an idea of how much power you get from a light field system and what you can do with that and how that is actually generating, didn't mean to go too far back, generating all these sub-aperture views. So that is how the camera works from a very top-level viewpoint. But what is more interesting is what you can do with that technology, because anybody that's shooting with one of these cameras isn't thinking about how the microlenses are interacting and how that's actually affecting the content. It's all about the storytelling and what you can do from a cinematography and from a visual effects standpoint. So I'm going to go through and highlight some of the most compelling things that you are able to do with a potentially future very high resolution light field video system. One of the core things, one of the core benefits is the fact that you now have within the refocus range infinite depth of field, meaning everything can be completely in focus. That has obvious implications for all the visual effects pipelines and workflows where you don't have to deal with defocus and the compositing process as well. But you can also then have everything be in focus that leads to the ability to then change your focus. So you've seen this in a lot of the other things that Lytro has launched and a lot of the software. But the ability to physically change and resample anywhere within the actual scene gives you the ability to have a shallow depth of field beyond anything that any traditional optics can produce. So you can think of a very large system giving you the capability of a shallow depth of field equivalent to something like an f.5 lens. Right? So that's something that if you asked a focus puller, they'd say, you're out of your mind, I can't focus that with a moving thing. I mean, the depth of field is just so shallow that you end up having to really make sure that it's on a motion-controlled stage or something like that. Whereas with light field, because it is a completely computational process, you can look at every single frame and lock focus perfectly on every single scene itself. Additionally, we also like to extend computational imaging just from the image itself into what you can do by having what we call volumetric flow vectors. And these are things that you can produce with sufficient sampling frequency that gives you the ability to computationally alter your frame rate without any artifacts. It gives you the ability to change your shutter angle completely without any artifacts. So if you take, for example, something like The Hobbit that was released in high frame rate for cinema, and they shot it generally with a 270-degree shutter angle, and when they released it for the 24 frame per second release, they literally took every other frame and threw it out. So that resulted in a shutter angle that had an aesthetic that was different than if you would have traditionally shot it at 24 frames per second, and that's by virtue of not wanting to shoot the entire film twice. I know I wouldn't want to shoot an entire film twice. But with light field, because you have these extraordinarily accurate three-dimensional flow vectors, you can regenerate every single frame and you can regenerate the shutter angle for every single frame and do that in a completely automated process once you lock in whatever the aesthetic is and how you want to tell your story using the shutter and using the frame rate as an artistic tool. One of the other really cool things about light field is the fact that we are massively oversampling our images. So within the single frame, you can actually sample multiple amounts of time, and you can sample different exposures within the same frame by virtue of having the theta and the phi directionality to the pixel structures. So with that, you can generate dynamic range that actually exceeds what any traditional 2D camera can do today. And then you can also figure out different ways that you can sample time in very unique ways that, again, you cannot do with any traditional 2D sensor that is determined to have an actual 2D image output. And these are all things that Lightfield cinematography can in fact produce. One of the other requests that we get all the time is by virtue of the fact that you now have an aperture that never stops down, right? So it's always an open entrance pupil. And with that, it allows you to have, let's say, something shooting by candlelight or outdoors by moonlight. You can have wide depth of field by moonlight, which again is just something that you cannot do in traditional cinematography. And we're really excited about those opportunities that give you really extreme low light capture capabilities. One of the things that we kind of covered in every presentation is the fact with one single lens, one sensor, you can produce any infinite number of stereoscopic baseline images. You can animate that, you can have it go completely flat, you can go to a very wide extreme, and if you configure your system appropriately, you can get a baseline that is beyond what any stereo camera rig would normally produce, meaning you can get well above 62 millimeters of a stereoscopic baseline. In fact, you could technically double that if you wanted, or triple, depending on the optics of your system. So we like to really show off that without having to do any additional depth processing, without doing anything, just by fundamentally resampling the light field from that entrance pupil, those little sub-aperture views that I was showing you, it gives you the capability of animating any interaxial baseline in addition to re-rendering it out for multiple formats, because obviously stereo geometry changes depending on what screen size that you're sitting, or your seating position, and what screen size you're viewing it on. So if you generate it for this size screen, then I could regenerate automatically to retain that same volume for a mobile size screen, or a laptop, or an IMAX size screen. And that can be all done completely in an automated fashion. One of the really compelling things and one of the core benefits of Lightfield is the fact that it completely eliminates the exposure triangle, right? Your aperture is always completely fixed and open. You don't have to worry how the shutter speed and the aperture interact with ISO. And because you have the capability of extending the dynamic range, you now don't even really need to worry about the ISO. You just have to make sure that your sensor is appropriately exposed. And beyond that, everything is completely computational to get every artistic benefit that you would want traditionally is now part of that post-production pipeline. And just to tell a little story here, I get asked all the time by cinematographers and directors, what does a light field lens look like? What does it look like? You know, there's lots of lenses that they'll use traditionally, and they have their favorite collection, or they go back to the same rental house and they have the brand and down to the serial number, and they like the way that it aberrates in a certain way, or that it's soft or has a certain warmth to it. And the reality of a light field lens is it's kind of like the unity gain in the audio world. It's the perfect master of the image itself because it has a very flat response. So the benefit of that is the fact that I can take any existing lens, so hand me one of these lenses over here, and I'm only showing this, I have no brand loyalty, it's because I had marketing rights to it, so don't ask me why. But with that, I can characterize that lens, again, right down to that serial number, and I can create an entire lookup table for any lens and any parameter, and from that single light field master, regenerate any optical parameter that you want from the light field image itself. And we find that to be one of the really compelling things, that you actually will capture the master footage from the light field, and then from that, you can use artistic tools to generate the lenses that you want. Or you can have your own, and you can characterize your own and keep it your own proprietary lens. That's up to you. Okay. Let's jump into visual effects now, because obviously these are all done in post. It's part of the production pipeline. But for visual effects, there's things that you can do with Lightfield that are really just unfounded creative benefits that increase efficiency dramatically. One of them, and one of the things that we're most excited about, is something that we call depth screen removal, or another way to call it is green screen without the green screen. And consider the fact that you have, from your scene, from the light field, an understanding of the exact coordinate in XYZ space of where every pixel exists. That gives you extraordinarily accurate segmentation for foreground, for background. So you can imagine a tool, your artist goes in and literally says, this is my foreground, this is going to be my background. It can segment that based upon the volume alone. And in addition to that, you know, the next question is, well, what do you do about edges and transparency and all these other things? Once you have your segmentation, I also know how the light goes behind the object. I know how to do foreground, background spill suppression, because I can see around every single object and every edge that exists in the scene. So you can see how this is actually going to get you the ability to get rid of your green screen. You can light your scene appropriately. You are able to then create virtually every single shot is a green screen shot, and you can recomposite, put things together. You can combine multiple light fields and put them into a completely new visual effects workflow. One of the other things that we're really excited about is by virtue of having the 4D functionality, you can actually generate an automated 3D camera track. And that is an extraordinarily accurate track that comes out of the system and gives you the ability to have that without having to do manual intervention. And again, the reason for that is because we have such high accuracy of sampling, everything is in focus, you can triangulate points more accurately than any other technology that exists, and you may have some other really cool hardware that goes into the system itself to support this type of a technology. But this could be potentially as part of the metadata format that you would use as the artist or as the visual effects community. One of the other things that always comes up is by virtue of having the volumetric flow data, if I'm an artist and I want to then trace out an object or something that's in the scene, let's say you want to do something with the wrist, I can actually create rotosplines that are dimensional. And that's because I know how every photon is moving in XYZ coordinate over time. Again, that's how I'm able to resample based on the different ways that you can sample the actual pixel itself. So you can automate the process of laying down a spline and watching it propagate through the entire sequence. So that's why I like to call it semi-automated, because you always want to have the artist interaction for any clip in visual effects. Again, because we have the volume, you also get, just as an automated pass, UV coordinates and the normals, right? So you can relight your scene by virtue of having the light field data. And this is, again, really no manual intervention. It's just an artistic pass of where do you put your three-dimensional lights inside of your scene and relight it accordingly. So that, we again think, is extraordinarily compelling, and it just frees you up to help tell the story and make sure that you don't have technical retakes by virtue of having different lighting scenarios or how you want to composite and interact with two individual scenes together. And this, apparently, we're making a cell phone commercial, apparently. But realistically, when you look at the DI process and you look at just how much work goes into the color for every film, and this is not just limited to the DI process, but because you have the volume, you're able to do a point-and-click interface that you're able to segment your image and perform specific depth effects based upon those regions. So I don't know how many times I've been in the screening room and they want to go in and add an additional glint to the eye. So they have to go in, they do a power mat, they do a rotospline or whatever, they outsource whatever they need to do, they bring all it back in, they apply the effect, and then they do that for literally hundreds of splines on the entire image. So when you combine that with the ability to have the semi-automated rotoscope, in addition to having the volumetric information, and you can do this in an automated fashion, it really is game-changing for the amount of efficiency and the amount of benefit that you get for all of the DI process or any of the color workflows. And then finally, we'd like to highlight for distribution purposes, you can have really completely infinite control over what formats you release and for what. So in cinema, obviously, you have 24 frames per second traditionally, or you go up to 48. They're talking about going up to 60, and you see some films that are shooting at 120. Well, with Lightfield, you can do that and then accurately regenerate the shutters that you would like in order to have the same motion blur that's consistent throughout every single piece of content, or change it if you want to do different types of formats for the home theater release. You can do that, and it's just literally a push of a button, and it reinterpolates the entire film in order to generate any aesthetic or any distribution format output that you would like. Okay, so that's a lot of data. So I'm going to take a break here and take a little sip of water, let you all digest that for a second, and I'll leave Lytro Emerge on screen because hopefully many of you have seen that already. So Lytro Emerge. What do you get when you actually start putting all of these things together? We're really excited about our technology in the VR space. When you look at all of the other VR cameras that exist today, we like to call it the Wild West of capture right now. You're seeing these plastic molded rigs, and you got GoPros and duct tape and chicken wire and, I don't know, cell phones, and you got some really crazy things that people are doing to generate really cool things, right? But the challenge is that you are not actually capturing a light field volume by virtue of as soon as you stitch to a spherical map of any sort, you have killed the volume. All you have there is one texture map, and if I move left and right, you really don't have any of that. I can move my head in space, but the parallax has been completely distorted. The lens and the origination source has been completely mitigated. So we like to rethink these principles from the ground up, and that is the point of Lytro Emerge. We think of this being the volume. So if you look at, you want the ability, and you've seen stuff from Otoy, where you had the ability to move left and right, the full 6 degrees of freedom. And we consider the light field volume to give you that full ability to immerse yourself in any environment. And that is where we think it is truly a compelling storytelling tool. And that is giving you the sense of presence for live action VR that is currently only available through synthetic data or from a series of 2,000 exposures, right? And this is the Lytro Emerge. Isn't it pretty? I mean, come on, look at that thing, right? And I'll just show a couple of the other screenshots that were in the announcement videos that we published a week or so ago. And this was not actually in London, but we have it there just so you can see it. So the full system will include the camera as well as the server and the storage and processing, and it was brought up in many of the presentations about just how much data and how much processing and how much storage that you really need in order to do compelling, immersive, 6 degree of freedom, light field VR content. It's a big mouthful there. You also have the software that enables all the editing, all the visual effects, and that gets integrated into existing visual effects tools and pipelines. We don't want to give you a new tool. That would just be kind of cruel to the visual effects team. You also obviously have the player that is allowing you to generate that full 6 degrees of freedom and basically compute that on the fly. And in the future, we also agree that going to the cloud is really the only way to make this a widespread consumer device and enabling that widespread across all, actually all devices itself. So with that said, I think I actually did this in the exact time I allocated. I want to take some Q&A while we got a couple of minutes left. And okay, yes?
So I think, unless you want this. No, you go ahead. Okay, that works. I will ask his question.
I will address your question, so.
Okay.
Go ahead.
I think what the question was how the volume of data as it would be generated by the acquisition system and then eventually working its way through the production pipeline to a deliverable, how that deliverable then can be manipulatable or manipulated or malleable in any way, shape, or form by and for any given display or presentation media.
Yeah, that's going to be a lot of data.
Right. So it is a lot of data. So let me start by addressing the stereoscopic, and I'm totally in sync with what your questions are now. So thank you for bearing with me. So yes, ideally you would want all of that data to completely transfer down to the end user, but unless you massively subsample that down to get to something that is a usable amount of bandwidth, a lot of that just can't be done, right? Just by today's bandwidth restrictions, because then you're imposing a data challenge to the end consumer. The current tool sets that we envision are more for the content creators to have that full creative flexibility. And then ultimately, in the future generation, it will go down to the consumer. But that is a much longer term investment in, let's call it cloud infrastructure, if that makes any sense. But with the increased amount of metadata, you can provide all the disparity vectors, you can provide the normals vectors, you can provide the flow vectors as a two-dimensional representation. By doing that, you actually do lose quite a bit of the flexibility. But in the future, when you have the amount of bandwidth at the consumer device itself, you can completely provide the full raw light field to everybody and everything. So that's my long-winded way of saying that it would be great to have that at the end consumer, but we're years away from having that kind of bandwidth. I'm going to give it to Paul here just because he was on the panel. So.
So a great presentation. One of the challenges of light field imaging is that if you take some of your early products, there's like, an 11 megapixel sensor here, but once you decimate it by that lenslet array, you actually only have like about 330 by 330 pixels in your image. And with some fancy math, you can get that up to maybe 700 by 700 or something. Mm-hmm. But for cinema, people want 4K. Mm-hmm. And to imagine having a lenslet array camera that gives you 4K in the end, you'd have to have like a gigapixel sensor for that. So what are your plans to get across that fundamental challenge?
I have to be really careful what I say now. The things you're saying are all correct. Yeah, with fancy super resolution, you can get around a lot of those limits, and you can break the diffraction limits and everything that you already know. But ultimately, you need a lot of resolution to get high quality 2K or 4K cinema content, especially when you consider the signal to noise that you need, the dynamic range, everything that goes into everything that we embrace in this industry. It requires a lot of resolution, and there's just really no trade-off behind that. So that is something that we may or may not be working on, and may or may not have an announcement. Okay, I see a big hand in the back, and I know I'm out of time. Am I good to keep? I got 3. Oh, I'm apparently over, and I'm going to get the hook here. Okay, well, we got the one more because I already pointed, and that's just not nice of me.
Okay, thanks again for the great presentation, by the way. I'm a big fan of your work. 2 quick questions. So it seems like the camera was pretty big, so I imagine the radius is probably 1 to 2 feet. So does that mean when I'm in the VR experience, I can only move my head about 1 to 2 feet sideways? And would it be possible to increase that potentially by putting, say, 2 or 3 of these cameras in the room and capture everything? And then the last question is, how much what was the bandwidth like to stream that?
All great questions. Okay, so the first thing is we haven't officially published the actual size, and everything he's asking is about Lytro merge, just to be clear, not about other things that we may or may not be doing. So you are correct that fundamentally, and all the other presentations support this, the size of the surface of a device itself determines what the full volume is that you can move within. So you could make a device that is 2 meters around if you wanted that. You can make one that is, a third of a meter, and everything in between. And the design of Lytro Merge is built in order to completely allow for customization and flexibility with our alpha and ultimately all of our customers. So your second question in terms of could you put multiple of these around? Well, of course, you just have to buy 3 of them, right? But then you would also be rephotographing the other cameras and maybe walls and lots of other problems.
You can use a parallax to correct those.
Well,
them out too.
Yeah, you can do some visual effects magic, of course, yeah. I think I answered your question, Zoe, and I'm going to get the complete...
I think the third one's the...
Oh, streaming data. That one's tough for me to do because that one hasn't been published either, but if you think about what Paul was asking, you can think about those types of data rates. They're quite high, but with some of the brilliance over at Otoy and getting a lot of the compression really down by reducing the redundancy in the data, you can actually make it in a much more appropriate footprint. For our content creation partners, they would have access to the raw data. And then what we do with that afterwards is more about how you get it into the player and into the interactive ecosystem. Okay. Now I officially have to step down because I'm going to get the hook here. But look forward to chatting more. So thank you, everybody.
So we had some great presentations tonight, going into some good detail and so forth, and hopefully if you didn't know much about Lightfields at the start of this, you have a little better understanding. So I'll go through and ask a few questions and so forth, and then we'll open up to the audience. Some of these notes I made some time ago, so things have changed. So currently, in terms of time frames for Lightfield cameras, we've, of course, have the still cameras that have been out for a few years now. Now, the Immerse, in terms of its time frame, is there an announced time frame that will be released?
A great question. Again, I have to be careful. So what was in our public release is that our early alpha partners will have access Q1 next year. And then throughout that year, there's multiple iterations that will occur, and you'll see it from that point forward.
Great. And in terms of the cinematography, is there any?
Again, have to be very careful, but sooner than you may think.
Okay.
Yeah,
All
to
right.
be nice and vague to everybody.
All right. Let's see. So in terms of post-production, final delivery, you've touched on that a little bit, I guess, and you guys are envisioning two different phases, as I understood it. That one would be that the director and post people go ahead and lock in their settings and their focus and the rest of it, and then generate basically a 2D or at least a stereotype of image, and then pass that down through traditional post-production process. And then the longer-term plan is to go ahead and keep that package together with all of that information so that visual effects and the rest of the pipeline would deal with the light field data as opposed to 2D data. Is that correct?
Yes, that's correct. One of the biggest challenges that you have when you're fundamentally this disruptive for a traditional workflow is when directors and cinematographers are on set, they make a decision, and that's the decision, right? So at what point do you actually modify the image, or do you allow for modification? And these are all things that you have to be very careful about to make sure that you can either lock the decisions that were made on set or make it locked as a post-process at a certain point in time, or depending on the studio and the production, you can have it completely open, but that gets into lots of other questions and issues. So
Right.
that's why you have multiple phases and multiple types of production environments that you could be working in.
Right. I mean, obviously one of the things we face in visual effects is the director's holding off on making any decisions till the very last moment. So one of
Always.
the concerns is we may give them more things that they could delay till the very last moment. So,
Yeah.
Paul?
So I want to make about light field photography. It enables all of these exciting things that you can do in post-production. Something that we care a lot about in cinematography is signal-to-noise ratio and how good your shadows are in your dynamic range and things like that. And there are a couple of places where you can't get something for free. And if you think about a traditional lens with a nice big, 2.8 t-stop on a good quality sensor, that's going to get you like as much dynamic range for really shooting that actual bundle of rays into each pixel than any possibility of actually photographing them all individually on smaller pixels or with little lenslets and then computationally adding them together after the fact. That's going to be a fundamental problem because of how photon shot noise works and the mathematics of all of that. So we need to look very carefully if we want good 4K high dynamic range with good shadow detail. That's the stuff to look to see if there's ways to solve those problems. And computational photography may come up with some interesting solutions for that, but we need to be careful about that.
Is your fundamental assumption there that you're using small pixels? And that's really where the shot noise is the problem?
If you're trying to compute an image out of lots of little pieces by effectively having broken up that light into little bins, binning all that individually and then averaging it together. Averaging it together gets rid of some of the noise that you have from all of those things, but you'll still end up with like a square root factor that you wouldn't have had if you just imaged it all into one nice pixel to begin with.
I would disagree from the standpoint that that is making an assumption that you're not using the same size pixel and having a larger optical format.
Okay.
Right. But you're absolutely correct. If you're trying to cram that many pixels into a 35 millimeter format and you've got 0.9 or 0.7 micron pixels, it's impossible.
There you go.
Yeah, you're right.
That's the point.
Yeah, totally agree.
Well, and I guess that was the other question that you guys touched on. Obviously, the original light field cameras were large array systems, and there's some advantages to that and some advantages with the micro lens type of approach. Do you guys want to talk about that a little bit, about the different trade-offs between those two different approaches, or?
You're first.
Well, I think it's really interesting. One format that we didn't talk about today, which is what I thought that this new camera from Light.co that a friend of mine, Karin is involved with, I think it's going to be like an incredibly cool camera, but I was assuming since I knew it was going to be made out of lots of little cell phone cameras, it was going to be a light field camera. And there's a little bit of light field stuff going on in there, but mostly what they're using is multiple cameras to give you higher resolution. But something that would just take, a good quality, iPhone 6s camera, and just make a good solid slab of them, you know, like that big or something, and just wire them all back and get your light field that way. I mean, the quality that you get with these little cameras is great. At that point, you'd be averaging a lot of pixels together. If you're happy, you know, almost happy with the noise you get off of one of these cameras, then once you average together a bunch of them, it'll be cool. I think that would be a pretty viable cinema camera like that with, you know, every 8 millimeters one of these guys.
So there's obviously lots of advantages there, right? That you don't have to worry about having crazy resolutions on one piece of silicon or anything like that. The disadvantages to an array is the lens, right? You have now dozens, hundreds of lenses that have to all be optical grade. They have to be characterized. You have to calibrate them. It's, from experience, it's not easy to do that. And then you have the challenge of what happens if one of them becomes moved or dislodged. And then in the big Stanford arrays, you obviously see how large those things are and have to actually have them very accurately calibrated. And if you think that the lens and the sensor are always at the exact same bore site in terms of the center optical axis, they're not. So you have to actually calibrate the sensor, you have to calibrate the lenses, and it turns into this multi-dimensional challenging problem. And assuming you can get that all lined up, then fundamentally the math does retain this, you know, is the same. So the advantage of using the microlens array is that the accuracy of each microlens individually can be much lower. They can be calibrated in a very automated process, and now you only have the one big main lens that you have to worry about characterizing. So there are many trade-offs and many benefits to both approaches.
Now, it seems to me Adobe at one point had done some tests with Lightfields, and they were using multi-lenses in front of a regular lens, kind of an inverse type of thing.
Yep.
And then they also did some further tests with micro lenses, but then they were at a different focal plane than the way you guys are approaching it to try to get higher resolution, as I recall.
Exactly right. Okay, so the inversion approach, the benefit there is you can use larger lenses, and you're effectively creating the sub-apertures directly versus using micro lenses. Lots of huge optical challenge, and you still have the problem of having multiple lenses, and you have to calibrate each one of them and figure out how all of them work together. But still a viable, really cool, interesting approach. And the reason that you would potentially put your micro lenses not at the physical focal plane itself is because at the focal plane, that's actually the point in which you have the lowest amount of resolution in the light field projection. So by offsetting it slightly, you can increase the amount of super resolution that you can produce, but it's at the trade-off of certain depth of field ranges. So there's lots of other ways to do it, and there's lots of amazing research out there. Yeah.
Okay, well, I guess the other questions are, you know, we've talked about light fields. How important or how useful is depth information? Obviously, you guys are using it, but in terms of just viewing depth versus creating geometry and so forth with depth, do we need to actually have the 3D data in terms of depth data to actually view the light fields in a sufficient way? Or does the depth allow you to get higher quality images combined with the light fields?
I can sort of field, you know, our approach, which is that, you know, when we're capturing anything, whether it's in a light field or in any other form, we want to know where the ray origin is. And so even if you have a light field and all these rays are coming in, you know, this is from 120 degrees, this is, you know, 90, 0, whatever, you still want to know where that's the source of that ray is. So in that sense, depth is important. But then I also feel like we want to know everything, like what is the, you know, where do the rays that lit this source come from? And so we basically are looking at it from the rendering perspective, but we want to actually map the light transport of a volume. And depth is a big part of that, as is, you know, the photons. So yeah, it is an important piece. And normals and all these other pieces are an important element, especially for VR, where it's like not just the window effect. We have to go and build, you know, giant walkable volumes, and that's challenging. So for that, we need a lot more information. And, you know, that's how we look at the problem and the data.
Great.
I want to add, you know, when you learn design sketching, and you draw a cube on a piece of paper, the first thing you learn is all the outside lines of the cube, you bold them up, and it punches it off the page, and it gives it apparent depth on 2D. I think we're going to start seeing effects like that in virtual environments, where every silhouette I see here, I could be putting little bounding boxes around it and punching it out and getting really surreal effects in the world. because it doesn't have to be an exact representation. So I think depth is another axis that we're going to start playing with from an artistic perspective that we don't currently think of.
Now, along those lines, and I think I'd seen some paper on somebody painting in a light field type of setup. I mean, is that type of creation beyond just photographic or just beyond computational computing? Is that something that you guys have had any experience or thinking about?
I'll speak to that with our entire tool set. You know, we started not necessarily with the premise of we wanted to capture light fields. We wanted to render them first. I mean, that was an important piece. And I think that even if you solve all the capture problems, you still want to put it into a rendering pipeline where you can mix, as the gentleman was asking, you know, the synthetic content, you know, captured content. And if you can do that, then you can create anything. You can take Tilt Brush, which Google just bought, which is on the Vive and the painting thing. You can put that in Octane and drive that live like you can with Motion Builder or Mudbox, and then generate a light field out of that or a volume. And I think that that's why I think rendering is an important piece. Of course, capturing is critical as well because there are things that you just can't create procedurally, but mixing both is important, and it's definitely the future of this medium.
Okay, well, let's see. Now, we've seen how visual effects have been done utilizing light fields and how you've captured the data and using those. And obviously, John, you've also pointed out with future technology that you guys may or may not be developing that could be used. I guess the question is, today, are there other applications of light fields for visual effects that we're not really using as much as we could or should be, just like Mark's capture of the stop motion and things like that? Are there times where we should be generating, even when we're doing, you know, dare I say, 2D type of things, non-light field, would it make sense to go ahead and photograph light fields or photograph objects or generate just objects so that we can work with them in a 3D space as opposed to simply rendering them from the one POV to match that specific shot?
So visual effects has been doing things a little bit like capturing light fields. And actually, we have in the audience Tim McMillan, who's now at GoPro, but back in the early 1980s, he was starting to shoot time slice shots of putting a whole array of cameras, photographing the scene all at the same time, and then you play it back as a movie, and it looks like, you know, frozen moment effects there, and it had some very nice ones that were even circular rays all pointing in, and that's something popularized by the bullet time effects in the Matrix. And I think there would be some really cool VFX possibilities with two-dimensional array of cameras. And now that, you know, GoPro has made it so you can get, you know, an image that is pretty good looking up on a cinema screen even, for a surprisingly low amount of money, and they're starting to be able to synchronize them. I think that you could creatively think of a lot of nice applications of shooting a full 4D light field and then creating a very interesting visual effect with that.
A way to think of the director, so light fields suck because there's just too much data. So somehow you have to winnow down the data and compress it and do things. To me, the cinematographer and director are a real-time data compression algorithm. They're saying, you know what, we don't need that, we don't need that, we just need this. In a way, Paul's example of just give me a really gorgeous lens. If I know that's the shot I want, then give me a gorgeous lens and I'll get that shot. There's just a tension in all the things going on where on one hand we have these complete 4D representations of everything, but in the end it's going to come down to content in a piece. And I think that's just a thread going through all these conversations of how to cut it down to actually get your final piece.
Right, right. Well, and that was certainly interesting seeing you guys comparing light fields versus a much simpler type of light field. And I guess that brings up, you've got things, other VR type systems like the Google Jump and the Jaunt Neo camera, things like that. And, you know, exactly if they're using light fields or how they're using it, you know, there's been different discussions or things that people have said. Do you guys have any thoughts about that type of camera rig and how much they might be truly utilizing light fields, or?
I do.
I do too.
Okay.
Comment on that. So, I mean, technically speaking, a single camera is sampling the light field. Did I just die here? Can you hear me? Okay. So I can have any one camera and say I'm capturing a light field.
Even a light meter is sampling the light field.
Right, right. So it's just a really terrible sampling of the light field. So as soon as you have more than one aperture, more than one camera, you're sampling more than one sample from the light field. So when you look at the Google Jump, which is actually a really pretty cool technology, and you look at what John is doing as well, it's more that they are sampling from the light field, but what they do with it is distilling it into a physical non-light field, right? Because it's now one texture mapped sphere where you have completely taken your lens and your multiple lenses and you kind of bastardize it into one big entrance pupil that makes no sense anymore. And you have no light field left, right? So you've got little slices of light fields that are all being blended together, but it's no longer the light field anymore. It's just a 2D spherically stitched image.
I think the case of jump, though, it's a left and right eye sphere with depth.
Spheres, correct.
And
Two
that's
spheres.
why if you move your head like 3 inches, it'll be like looking at a pop-up book.
Okay. Great.
Cool technology, I love it.
So I guess then the question is it, and I understand that purpose for the Google Cardboard and so forth, but obviously like Otoy has the light field player, been working with that.
Yeah.
So I guess, is it possible to get out of the Google assembler, as I understand it, where somebody uploads the 16 cameras, could I get back a light field data set that I could use with, if I had my own light field player? Right, okay. I gotcha. Okay, yeah. So as long as you had a multi-camera system, you can get a certain quality of light field from that.
Correct.
Well, I would draw the line at whether you have a 4-dimensional data set.
Okay.
And if you have a 1D array of cameras, that's a 3-dimensional data set. So that's kind of a deficient light field. And as far as being able to just through the rays that you captured, be able to push your view forward or pull your view backward, you can do that correctly in the horizontal dimension, but incorrectly in the vertical dimension, because you don't have any rays to grab from those other
That was
points
the
of view.
squishing block.
Right.
Yeah.
So
And so there are okay things to do with these kind of degenerate 3D light fields, but a real light field is 4D. It's got to be a 2-dimensional array of 2-dimensional images, which like the Lytro cameras actually get that, and it's great at
Can I
that.
point out what it's like working with Paul when you do an approximation and he calls your work degenerate? It really hurts, you know?
I'm glad I didn't say that.
So is there a minimum, I guess it's the question, to create what you would consider a true light field? Do we have to have 3 layers deep or 6 or?
I'd like to see at least 3. And, so like the Otoy light fields, those are 72 around and 24 up and down. It's a very rich sampling. Effectively, the views are 3 centimeters apart. And with, the processing that Otoy is able to do, you get a very continuous point of view for about a meter of sphere. So, it takes good cameras and some time to capture that, but it felt like the right level that we need for today's and the next generation of VR.
And to add to that, we took part of Paul's design for that big GoPro rig, and we built a video version of the static light field. So we didn't do the full sphere because that would be $800,000, but we did a part of it, and it works. Like basically what you guys saw with the static thing out there, we can do video, and it's a cost thing, and it's like how much do people want to spend on this? I feel like the solution is probably not to go spend $800,000. It's to basically get what you really want, which is I want a holographic representation of the scene, the people. Those are all different tools. Just like you don't necessarily, treat a close-up shot the same way you treat a, wide-angle shot. And I feel like we want to support as many of these different layers as possible for content creators.
Okay, great. I guess a question about the Lytro VR system is, can you talk about how close we can photograph something? Is there any type of range? Because as Mark points out, a lot of that intimate type of thing, and as well, with stereo, is trying to get something somewhat close. And that's been part of the problems with a lot of the stereo VR rigs, is they still have to be, at least 4 feet away or 6 feet away. Otherwise, you get problems with that. Is there?
And I have to be very careful. The system is built to be very customizable and flexible, right? So in order to get to very close proximity, your density has to go up to a very high number. So the answer is yes, the plan is to have the ability to photograph at close objects, but it is depending upon a lot of the alpha partners that we have.
Okay, great. And we talked a little bit about dealing with light fields in some of the different tools. I guess the question is, if I've got something like Nuke and I've got a data set, from whatever camera system or rendered out by Otoy or whatever, can I render that and view that today in Nuke, or am I going to need special types of plugins, or is that something reasonable that you guys are looking at? And
so in our case, the Nuke plugin is already out, and you don't just have the ability to look at your renders, you can actually fully render. I mean, the entire render is built into Nuke, and you can basically create different layers with that. And there's a question about how we're going to bring these light fields or these volumes into Octane. So with version 3, which is on our web page, you can play with a demo. You can load an open VDB volume. You can basically look at any volumetric data set, but we can also support these kinds of captures. And the idea is that it's not just viewpoint reprojection. You also have enough information to relight it, the normals, the albedo, the specular, all of that is in there. And then it becomes simple. I mean, it's the ideal content creation tool. And then if it's Nuke or After Effects or whatever it is that people want to build on our SDK, all those things become possible. And they get also exported in a form that is not quite as noisy as the raw capture. We can basically treat it like a synthetic rendered light field, and that means that we can compress it better, stream it better. That's a big part of how we imagine this getting to consumers soon, is by putting it through that, through that system, and also helping content creators at the same time.
Okay, great. Oh,
I have a question.
sure. Tim?
Speaking of visual effects, could you address the smooth surface problem and depth map generate? Probably reverse.
Let's see. So if I think I understand it, so getting depth out of a light field, right? I mean, you can get depth out of a stereo pair, and a light field is like lots and lots of stereo pairs all over the place. So you can get more robust depth for that. From our experience in relighting applications, it's hard to take geometry that's only taken from stereo correspondence and relight just from that. And when we do light stage scans or reflectance field capture, we're lighting from lots of different directions. And that tends to reveal a much higher level of surface microgeometry and specular versus diffuse reflections than you get just off of the geometry that you could theoretically get out of even a good light field. So I think that just for relighting and doing that, cinema quality is going to be tough to do that straight out of a light field. And I think matting as well. We have people here in the room who know really that a good matte is a very special thing, and they're hard to get. And doing that out of there's probably some good ways to get maths out of Lightfields, but you really have to think about what kind of resolution that you've got in there. That'll be some interesting computational imaging to do that.
I want to point out one thing. When you guys saw that video of the woman lifting her head, and that was this super high resolution, normal in motion, I mean, that was basically, I think, 1 or 2 cameras and many lights. So the point is you can flip things around and you can have more lights, less lenses. Sometimes you'll get better data out of that, and that's something to consider.
I'll just tack on to that, for Lightfield, you generally are assuming that it's a Lambertian surface for any type of relighting, unless, of course, you have other things that are doing other types of sensing of the scene itself that are integrated into the technology. So like other lighting, or you can do other things with different active illumination, those types of other technologies as well, and that can get you to a much more accurate level of understanding of how the surface responds to light. So it's not any one solution that gets you all the way there.
I'll just ask one more question, and then we'll open it up. In terms of it, if somebody's interested in Lightfields, is there a book or reference, or how would people start experimenting with Lightfields today?
These guys wrote the book, but
By the Alien, I mean, that's a good starting point, right?
yeah.
Which one?
Their camera.
Oh yeah.
I mean,
Oh,
like,
grab
we-
yourself a Lytro. For displays, grab one of those Leia 3D things, and you're really looking at a light field for reals. Ramesh Raskar et al. Wrote a book called Computational Photography a few years ago, and that covers quite a bit of this stuff. And you can go to the Stanford Lightfield archive and download their LIF viewer, LIF viewer, LIF view, and play around with it on the computer.
And Lytro also has power tools. That's a kind of a way that you can completely exploit all the camera parameters from the Lytro Loom. So that's free. You can download that.
Great. All right. Questions? All right. Great. Good. Now we've got some questions. All right. Let me go ahead and start.
Would it be fair to say, as I'm just getting my head around Lightfields, that I specialize in virtual production and motion capture, which kind of takes place in the middle of the pipeline. Sometimes you've got a plate coming in, and ultimately need to get assets into the renderer. And it almost feels like Lightfields extend the virtual production pipeline all the way in either direction to really sort of complete the soup to nuts. Am I seeing that right? Is that fair to say? Like, things are flexible. Like, the power of virtual production is that everything remains flexible for the sake of the camera and the story and the editorial and the composition. And this now extends that flexibility all the way to the end and even before the traditional virtual production pipeline. I'm just wondering if am I seeing that right?
I think
Is that
that's
fair
fair.
to say?
I mean, I think we look at these sort of multi-dimensional capture rigs, and whether it's Lytro's cameras or the light stage on these different endpoints, as being really important tools for synthetic production that is basically taking virtual sets, real things, mixing those things together. And I think there's going to be another really important piece of all this, which is when you go to VR, you're not rendering to images or spheres. You're going to have to render something that is kind of like the holodeck at some point, and it's not going to be a video game engine powered by Unreal or Unity through OpenGL. So that's where all these pieces really converge, and they become critically important.
Yeah, the big difference is also that while you do have that benefit that does go both backwards and forwards in the production pipe, it is theoretically from either a single viewpoint, even if it's a full 360, or from a camera. So you really aren't seeing behind and around like you would in a traditional mocap stage. But from that camera's point of view, it is in fact, I mean, it's the entirety of production. You can do anything from all the camera parameters all the way through the visual effects. I mean, it's all inclusive, you're right, but you don't have the full around.
And if you think about the amount of expense that goes into composing a shot that you're shooting for a movie, of having the people in the right place and the right makeup, doing the right thing and the right lighting, how could you afford to only shoot that with one sensor? I mean, grab everything you possibly can while you can, because this is expensive stuff.
Like if you had a light field as your plate and you wanted your actors slightly higher in the frame, you could use the depth to sort of pull it out and move it around to some extent. You have a little bit of flexibility.
Yes, yes, and that flexibility is limited by what type of lens you're using and the optics and the sensors, yeah, of course.
question that I've been thinking about in the context of cameras that we've seen in the light field industry, and we've seen cameras where you have a flat plane of a planoptic array of lenses, and we've seen spherical cameras where there are an array of cameras in a circle. But I'm wondering why we haven't seen a camera that looks more like a Ricoh Theta at the center of a planoptic disco ball of lenses, since that might be more economical to produce than one where you're using hundreds of cameras to get the same effect. Just wondering what kind of logistical issues might be getting in the way of something like that.
I think that sounds super fun, and you should build it. I think that the challenge is, the Ricoh Theta has, whatever, 5,000 pixels around, and once you decimate that into all the little balls, lenses that would be around it, which could legitimately get a spherical light field, you just be at a very, very low resolution. So that's why you put multiple sensors out there.
And the disco ball volume also isn't necessarily as big as you want. You want a bigger capture volume if you can. It'll get you more interesting coverage.
Comment and then a question to Scott's point about directors who can't make decisions, the whole idea of them being able to decide later in visual effects, and then it goes to whatever this new DIT person would be in DI, who would be making decisions on depth of field and everything else. Permutations are mind-boggling on how they can delay everything to the very last second. So that'll be a lot of fun. And go ahead.
So in a way, virtual reality delays it to the user.
Yes, I agree with that.
The question is regarding the Lytro and HFR. You made it sound like any frame rate is possible, independent of shutter and ISO, but aren't you limited by how fast a pixel can, bucket in and bucket out all the information?
Yeah, yeah. So it's not like you have to have a certain sufficient sampling frequency, right? But again, I have to be very careful what I do and don't say. So is your question in terms of what are the limits, or?
Limits and how? How you get different frame rates from what is.
Well, so I guess my question back to you is your assumption that you can't read out at 100, 200, 500 frames per second? Is that your assumption?
That assumption is predicated on that you're not using different portions of the micro lenses to have different time spheres.
Yeah, so you can, without going into too much of the technology, you can play with what is the sample time and the integration time on a per pixel level, as well as have extraordinarily high sampling rates. So you can break that boundary. There are always, of course, limitations in terms of how fast can a sensor physically refresh. But if you can sample at high enough rates, you do have a very wide range of, from effectively the volumetric flow that you can generate. And that's what enables you to reproduce based upon having multiple time samples within the same readout. Right? And there's different ways to do that.
I mean, the experiments that we were doing with video capture, and this goes back to the high-speed cameras we've been testing with Lightfields, is that if you get to over 200 frames a second, and you do optical flow, and you have sort of things like material separation where you can really start to triangulate details in the scene, that's pretty good. I mean, the optical flow vectors temporally will give you the ability to resample from 240 to 2400 potentially, and that's kind of the data that you need anyway if you're going to be doing UV mapping from a person's face frame to frame. So that's the kind of problems that kind of get solved by doing, however the approach is, you do want to sort of track every pixel, every surface, every fragment temporally, spatially, and that will get you this upsampling both temporally and spatially and from that data.
Yep.
Okay. Yeah. Is this on? Yes. Tim McMillan. I just wanted to make one observation that if visual effects people are grappling with how can we use this technology, one huge and glaring and obvious application is in digital set reconstruction. the amount of money and time and effort that's spent on recreating sets or getting digital artists to recreate, bits of sets that you've lost the data to, or you've got a 2D image, you don't know how it looked in 3D, is huge. And to be able to shoot your set, your scene, your environment with this technology solves a huge lot of problems for visual effects artists.